Calorimetry is a technique that measures a temperature change and calculates the amount of heat that is either absorbed or released during a chemical reaction. When we do calorimetry experiments, we're going to name whatever we are focusing on as a system. So usually that's going to be your reaction itself, either the reactants dissolving or reacting together, or the products that are being formed. And the surroundings will be everything besides the system. There are two types of calorimetry experiments that we're going to talk about. On the left, we have a coffee cup calorimeter, and we just use a coffee cup because it's a good insulator, so it keeps all of the heat in. The reaction is going to be done within the coffee cup, and then the temperature change is going to be measured during the reaction. For this type of experiment, our system will be whatever part of the reaction our problem is focusing on. So again, either the reactants dissolving or reacting together, or the products that are being formed. The surroundings will be the water or the solution that the reaction is occurring in. On the right, we have a bomb calorimeter, and that's a little bit different. Our reactants are placed inside of a smaller container and ignited, and that's occurring within a larger calorimeter. This is usually used to calculate how many calories are in your food. We don't actually have a bomb calorimeter to do this, but one of your problems does talk about bomb calorimetry. So the biggest difference between a coffee calorimetry problem and a bomb calorimetry problem is your system is still going to be whatever part of the reaction your problem is focusing on, but the surroundings will be the bomb calorimeter itself. So you will be given information about the calorimeter, such as the specific heat of it, in order to calculate your delta H for the surroundings. So just as a review, heat flows from hot to cold. When you combine two substances together, heat will flow from the warmer system to the cooler system. And we used Q equals negative Q to show the amount of heat that is transferred between systems, or between a system and its surroundings. It's the same amount of energy that one system is losing, that's going to have a negative Q, and the other system is gaining, so that one will have a positive Q. In an exothermic reaction, heat is being released, which means Q is negative, and because delta H is Q over moles, negative Q means that you will have a negative delta H. Now, because you are losing energy in the reaction, you're going to start out with more energy in the reactants, and you'll have less energy in the products. And energy will be included on the right side of your equation because it is leaving the reaction. For an endothermic reaction, heat is being absorbed, so Q will be positive, and delta H will also be positive. Now, because you're absorbing heat in the reaction, you're going to start out with less energy in the reactants, and you'll end up with more energy in the products. Energy will be included on the left side of your equation because it's being absorbed, so it's going into the reaction. Enthalpy is the internal energy or heat of a system at standard conditions. The enthalpy of a reaction, or heat of reaction, delta H, is the change in enthalpy during a reaction, so the amount of heat that is absorbed or released per mole during the reaction. Again, delta H is Q over moles. It can also be calculated by taking the enthalpy of the products minus the enthalpy of the reactants. Now let's do an example problem. This lab-based problem says Susan wanted to know how much energy was in her macadamia nut. So she set up a can of water above the nut and lit it on fire. She basically transferred the energy from the nut to the water in the can and calculated the heat of reaction by using Q over moles. Now, to figure out the Q of the nut, we're going to first determine the Q of the surroundings, which in this case was the water in the can. The amount of energy that the water absorbed was 4,598 joules. And we'll just assume that that amount of water, that amount of energy, was the same amount of energy that the nut released. So we'll use Q equals negative Q to determine that the nut released negative 4,598 joules of energy. Now, to figure out the moles of the nut that was burned up or used, we're going to take the initial amount minus the final amount, which gives us 0.4 grams of nut that was burned up during the reaction. Now, normally, to convert from grams to moles, we would use the molar mass of our substance. In this case, we can just use the made-up molar mass of a macadamia nut, 50 grams per mole. That would give us 0.008 moles of nut that was burned up or used in the reaction. For a total of negative 575 kilojoules per mole for our delta H. And that should make sense because this is an exothermic reaction, so our delta H should be negative.